Hello, my name is Nick Zhang, and I'm the lead for RC subteam under Dr. Siotras's VIP team, Active Safety for Autonomous and Semi-Autonomous Vehicles. Our team aims to develop a small-scale autonomous vehicle platform with sufficient onboard processing power to navigate around the track without external computing resources. So why do we do this? Well, students who study robotics need actual robots to test perception algorithm, localization, control algorithm, to practice low-level communication with embedded systems, etc., etc. The same goes for researchers and hobbyists. The real question is, why do we want to make our robots kinematically similar to cars, and why do we want to make them so small? First, why cars? If you look around the low-cost robot platform students use in a classroom setting, they are predominantly two-wheel differential robots, which means they have two motor-controlled wheels that can be actuated independently. This allows them to achieve forward, backward, and rotational movement. They can achieve almost anything, but not in a very exciting manner because they are not designed to operate at high speed. They can operate using their simple dynamics in a quasi-static state. This also means they cannot be used to explore real-time high-performance algorithms because very soon the movement speed of the robot would become a bottleneck and there's no incentive to make even faster algorithms. And they're not sufficient to simulate the rich dynamic behavior of a real vehicle. So what makes them small? A simple fact is the smaller the vehicle, the cheaper its operation. Right now the cheapest platform still costs around $5,000. While this is not expensive for researchers, it is impractical to assign one to each student in a class. Also, most platforms have full desktop computers with advanced graphic cards, and they are not necessary in all projects. Therefore, it makes sense to have a smaller, weaker platform in exchange for greater accessibility. With a palm-sized vehicle, it is possible to assign each student with one individual platform and set up a test track that will allow multiple vehicles to race together in a small lab space or even in a living room. So what do we want? We want cheap cars, which means the cost for making each individual platform should be less than $200. We want easy cars, which means easy to carry, easy to configure, easy to use, easy to operate. We want fast cars. Our current vehicle can go for 10 miles per hour easily. While it doesn't sound like much, remember we are very tiny cars at 1/27 scale. And if we scale it up, it would be 270 miles per hour, which would never become a bottleneck for any kind of algorithm we are running. We want many cars that is possible with our low-cost platform. With many different cars operating at the same time, we can explore the adversary robot concept. We can experiment with cooperation. We can have students racing their algorithm together. We also want them to be our cars, which means we have full control over every aspect of the vehicle. Many of the currently available popular platforms are built by putting computers and commercially available sensors on top of a already mature RC race car chassis. And these race car chassis are usually not designed to handle this extra weight, and therefore they suffer in dynamics. We hope to have better control over every aspect so we can better tune our system to have better dynamic response. Here are some iterations of our platform. In the beginning, we simply stacked off-the-shelf electronic modules onto an off-the-shelf chassis. It works, but the cable makes the car very messy, and we could never find an elegant way to arrange all the various components we have. As a result, we had a large, heavy, awkward car with terrible vehicle dynamics. In subsequent iterations, we designed more and more components ourselves so they can fit better and the whole assembly can shrink down considerably in size, and we have a neater platform. A major portion of the effort to shrink down in size is to design a new custom PCB board that substitutes every module that we use. This includes a DC-DC power module, motor controller, IMU sensor, low-level microcontroller, etc., etc. It is worth mentioning that the team is made up of undergraduate students exclusively, and when we decide to make a custom PCB board, nobody in the team has any experience in circuit design. We started by soldering the modules together and then transferring more and more functions onto our own PCB. As we accumulate experience, we became progressively more ambitious, and now we're using an industry-level system-on-board module that requires us to design a computer motherboard to provide peripherals for its successful operation. Here are the two most recent iterations of our PCB board. They are almost identical in function and performance, but the one on the right is a stack-on board that is designed to attach on top of a regular Raspberry Pi, and the one on the left uses a stripped-down version of Raspberry Pi that allow us to eliminate useless connectors like USB, Ethernet, and HDMI, and therefore further reducing size. The bottom left picture shows the signal traces of this board, and it was a challenging board to design because it has sensitive signal traces that must have matched impedance, and also very noisy high-power motor controller, and the resulting board is barely larger than a credit card. Our effort to shrink down in size is not limited to circuit design. We also have the ability to design a complete vehicle chassis. The pictures show the CAD design and an actual result of our prototype chassis. It is a rear-wheel drive chassis with stamping in the front and back. By designing our own chassis, we have more degrees of freedom in achieving a better integration of electronics and mechanical components. Although our primary objective is to create a platform, we also develop complete control pipeline to test and showcase our platform. Here we show some heuristically generated trajectories for our vehicle. We're also working on a machine learning based algorithm to further optimize trajectory and minimize lap time. We have a modular racetrack that can be assembled in multiple ways to compare our performance in simulator and in reality. Recently, we finished the real-time visualization of our vehicle with location information retrieved from a visual tracking system. Here, the vehicle is attempting to follow a trajectory, and the lap time is displaying its real-time location. Many teams are working on similar platforms. Earlier this year, Amazon released their Deep Racer with supporting software for simulation and training. MIT has a popular race car platform. But these are still large, relatively expensive platforms with suspension structures not suitable for high-speed on-road driving. ETH Zurich has a similar project with one 43 scale vehicle, which is quite smaller than ours. But the vehicle itself does not have any processing power, and the chassis does not allow for much adjustment. Therefore, I believe our platform can still fill in a gap that is not currently fulfilled by any other available solutions. Currently, we're working on the latest version of our PCB and design a better trajectory optimization method. We're also attempting to reduce latency in various parts of our control pipeline and complete a real-time localization algorithm that will allow us to run independently of our vision tracking system. That is everything I have. Thank you very much.